Section 7.5 is on page 309. Talks about homogeneous linear systems with constant coefficients. So consider a matrix equation x prime equals ax, in which A is a matrix, right? So this is kind of like identical if you recall. So this is a note, this would be the same. We're following the same steps applied to the system as if I had x prime equal ax, and I'm talking here about x being an independent variable, not a vector. Wouldn't this mean x prime over x equal a? And if you integrate, actually even faster, wouldn't you say let y equal e to the rx, and that would be r e to the rt minus a e to the rt equals 0. E to the rt cannot equal 0, it has to be r equal a, and my solution would be y equal e to the r. Actually, I know I messed up on all of this. Oh boy. There we go, much better. We would let x equal e to the rt. There we go. I'm so stuck on y. And x would equal e to the at would be a solution. And if you recall, if a is bigger than 0, this is exponential growth. And if a is less than 0, this is exponential decay. Right? So we're going to do the same here, but matrices don't behave like numbers. Instead, you took linear algebra, you know how this goes. Well, here, we're going to go for similarly. Similarly, for n equations in a system of equations, we say, well, let's see. If I take ax to equal 0, assuming the determinant of a does not equal to 0, x equals 0 would be the only equilibrium solution. Right? Now, is the system asymptotically stable? Is the system asymptotically unstable? Kind of like what we did back in the days. So this is how it works. If they give us x prime equal ax, just like here we let y equal some multiple, here we let y equal some e of e to the rt, a vector, instead of y equaling c1 e to the rt back in the days. So here, oh my god, back to the same problem. I apologize. I'm so stuck on y. So here we need to find two things. We need to find r, and we need to find this vector, which is the constant vector. So if I come in and say, well, let's see. If I take a derivative of this, that would be that vector r e to the rt equaling a that vector e to the rt. And if I divide by this and eliminate that, I could do that. That pretty much undo each other. And I'm sorry. If I divide by e to the rt, those eliminate each other. And now I'm looking at a vector times r equaling a times that vector. That's identical to me saying, you could do it two ways. I could say this is I could say this is AE minus ER equals 0. Or I could say ER minus AE equals 0. This author prefers this. So if I take this piece, that's the same as you figuring out the determinant of RI minus AE equals 0. So basically, since this cannot be 0, that's the coefficient, otherwise it's trivial, it has to be that the determinant of Ri minus A equals 0. And what that allows us to do is find the famous R's for the solution and proceed with that. Now, I'd like to look at a problem. Here's a problem. So, we're going to go after part B only. It says, in each problem 1 through 4, find the general solution of the system of equations. Part A says, draw a directed field. We're not going to worry about that. You're just going to do B. And C, I'm doing for you, but you don't have to do it. It says, draw a few trajectories. I use software to really do this. You just have to worry about part B. So if I look at B, it says, find the general solution of this system. So this is x prime, this is x, and this is A. So pretty much if I find the determinant of Ri minus A equals 0, and keep in mind how this works, the I for a 2 by 2 is 1, 0, 0, 1, minus A, which is 1, negative 2, 3, negative 4. You must have did that over and over and over. And I want that to equal 0, which means it's going to be the matrix R minus 1 and a 2 and negative 3 and R plus 4, the determinant. That's the notation for the determinant. I want that to equal 0, so that will be R squared plus 3R minus 4 minus a negative 6 plus 6 equals 0. That's R squared plus 3 plus 2 equal to 0. So that is R plus 2 into R plus 1 equals 0. So I get R to be a negative 2 or a negative 1. That's very good. Now what? Now I need to find the solution. So this is explaining how to get that. Now, if I look at, I pick one of those. Let's say R equal negative 2. Well, what that means, I'm going to take this and solve it now. That would mean that I'm looking at a negative 2 minus 1, negative 3, negative 2. That was a 2. Negative 3, 2, and a negative 3, 2 times x1, x2, and I want that to equal 0, right? The 0 vector, really. So doesn't this mean if I take equation 1, negative 3x1 plus 2x2 equal a 0? That means 3x1 equal 2x2 if I move this over. So here, if I really let x sub 1 be a 2, right? Actually, I could go this way. I could say x1 equal 2x sub 2 divided by 3. There's nothing wrong with you saying if x sub 2 is 1, x sub 1 is 2/3, but you know from linear algebra, they never do that. So there are many options I could do. You could have also solved this and said, you know what? No. x2 equal 3x1 over 2. And you could have said if x1 is 1, x2 is 3/2. That's fine. It doesn't matter. The book will do neither. The book will actually go for solving for x1 always and say, you know what? If this is a 3, they want integers. x1 will be a 2. That's what the book will use. Any of those will do. Any multiple of those will do. If you multiply this by 2/3, you get that. If you multiply this by 1/2, you get this. Remember, any multiple, any linear combination will do the trick. It doesn't matter. But they're going to take the integers. You don't have to, but I suggest you do that if you want to match the back of the book. And they always go this way. And if I take r equal negative 1, then I'm looking at, if I put a negative 1 there, that is negative, negative 1 minus 1, that is negative 2, 2, negative 3, 3, x1, x2 equals 0, 0, and that means negative 2x1 plus 2x2 equals 0. So that means x1 equal x2. Here it's very simple. Whatever x2 is, x1 is. And that would be the span of that. So in this case, I would say let x equal, so I found those vectors associated with each. With the first one, it's going to be 2, 3, e to the negative 2t. And for the second one, plus 1, 1, e to the negative t. Now you could combine those, right? And remember that this is going to be any multiple of that and any multiple of that, just like we did back in the days. So it's pretty much identical to what we did. Now, the graph of that, part C of that, I did on, I can't remember where I did it on. I think I did it in Maple. That's what it looks like. And do you see that everything is going to eventually be mapped down to the origin no matter where you start? And that's, we know from this that those are what? Asymptotically stable. Right? Okay. Another problem, numbers 5 through 6. Part A, draw a directed field. We're not going to worry about that. Part B, it says the coefficient matrix has a 0 eigenvalues. Now, I didn't mention it. Those were the eigenvalues, in case you missed it. And those are the eigenvectors. Remember those? So, matrix has 0 eigenvalues. As a result of the pattern of trajectories is different from those chosen from the text. Let's go again. Part A, you don't have to worry about that. Let's go after part B. Find the general solution. Well, to us, it's not going to really matter how they do this. The way it's going to work, we're going to pretty much let x equal e to the rt. All what I have to do is find what those are. And it's going to be c1 times the eigenvector associated with the first eigenvalue. So the trick doesn't get old. And why is that important? Because it solves differential equations using eigenvalues and eigenvectors. So pretty much I know the drill, the determinant of a minus. Now you could do a minus ri. This book likes ri minus a equals 0. That would be 3 r minus 3. That's why they put it that way. R minus 3 and negative 6. And this will be a 1 and an r plus 2. I want that to equal 0. That will be r squared minus r minus 6 minus plus 6 equal to 0. So that's r into r minus 1 equals 0. That's r equals 0 or r equal a 1. Very good. If I want to find the first solution, let's say r equals 0. Well, that would be, if you put a 0 there, negative 3, negative 6, 1, 2, times x1, x2 equal 0, 0. And if I take the second equation, x1 plus 2x2, you know it doesn't matter which one you take, right? And that would mean x1 equal negative 2x2. So if I let x2 equal 1, x1 will be a negative 2. There it is. That's the first eigenvector. And if I go for the second eigenvector, if I say let r equal 1, well, now I'm looking at what? R equal 1. If I put a 1 there, that's a negative 2, negative 6, a 1 and a 3 times x1, x2 equal 0, 0. That would indicate that if I take the bottom equation, x1 plus 3x2 equals 0, that means x1 is negative 3x2. So if I let x2 equal 1, x1 will be negative 3. And there it is. And my final solution to this would be x equal, So I'm going to take the first vector again. It's going to be C1 times negative 2, 1, but e to the 0t is 1, right? Plus, and if I go for the second vector, it's going to be C sub 2 times negative 3, 1 e to the t. Or I could simply ignore that and just say there's the solution. And I graphed that for you, and that's what it looks like. It depends on where you start. It depends on where you start. Whether that's positive or negative, it might reflect, but you see that this is kind of running left and right. And we have one more. Okay. And solve the initial value problem. Describe the behavior as t approaches infinity. Okay, here, the difference between what we did and what we're doing now, they give us initial conditions. We could find C1, C2 like we did in 7.4. So we start off with the traditional. We're going to let x equal e to the rt, which is going to be C1 times a vector e to some power, plus C sub 2 times a vector e to some power of t. And we're going to solve determinant of Ri minus a equaling 0. Sorry, I just knocked this thing down. And that's going to be 5 minus r. Again, I remember why they wrote it that way actually. It is going to be r minus 5. R minus 5 and a 1, and it's going to be a negative 3 and r minus 1 equaling 0. That would be r squared minus 6r plus 5 minus a 3 minus a negative 3 plus 3 equals 0. That's going to be r squared minus 6r plus 8 equal 0. And that would be r minus 4, r minus 2 equal 0. So r equals a 4 or a 2. Very good. If I start with r equals a 4, that would mean I'm looking at a negative 1, 1, negative 3, 3, x1, x2 equal 0, 0. That would be negative x1 plus x2 equals 0. That means x1 equal x2. The eigenvector associated with this, if y2 equal 1, y1 equal 1. I want to my second, if I take r equal 2, I will get negative 3, 1, negative 3, 1 times x1, x2 equals 0, 0. And if I take negative 3x1 plus x2 equals 0, that would mean x2 equal negative 3x1. If x1 is 1, x2 is a negative 3, or positive 3. Same thing. Now, I do know what the solution looked like. The solution looks like, so I already filled in the blanks. This is 1, 1 e to the 4t, and this is 1, 3 e to the 2t. That's the actual solution, right? Now, if I go ahead and say, well, x of 0 is going to be, this is really C1, C1 plus C1, 3, C2, 3, C2, and that's going to equal 2, negative 1. So basically, I'm solving systems of equations. Okay, I can get that right. If I take negative row 1 plus row 2, put the result in row 2, I will be looking at C1, C2, and a 2. My negative C1 plus C1 is 0, negative, that's 2C2, and negative 2 minus 1 is negative 3. So here I get C2 equal negative 3 halves, and that means C1 minus 3 halves equal a 2, C1 equal 2 plus 3 halves, which is 3, 4, 7 halves. So my final solution to this problem, including initial values, is x of t really equals, so C1 was 7 halves, 1, 1, e to the 4t plus minus 3/2 1/3 e to the 2t. I could write this a bit differently. This is all you have to do. I just want to show you how this looks normally. You could say that is 7/2 e to the 4t minus 3/2 e to the 2t, 7/2 e to the 4t minus 9/2 e to the 2t. You don't have to, that's what it is. So again, the case here, are those repeated? Are those distinct? Are they complex? 7.6 talks about complex, the last part, but we're not going to be able to do that. So there's the homework. And that concludes this section.